Welcome again to Centers, and grab something nice to drink again. And I still have my same cup of water, Chino. For you, it may be a different day, a different month, or even a different lifetime, if that makes sense. So now we're going to talk about the center when we use a different kind of metric. The expected value we discovered was only special, or was only a reasonable center, if we were using the squared spread as our metric. What if we used a different one? What if we used this one? The absolute value. I like this one because this is the intuitive one. And I'm going to bring back my beautiful picture. Reduce, reuse, recycle. And we interpret this absolute value one with the pink lines. So the spread, we're measuring it linearly in the sense that if we measure the straight line distance and use that as our spread. Okay, so this one I don't have a nice proof for. I mean, I have a nice proof, but it's kind of restricted. It's not so general. But I'm gonna show it anyways. And if you have any suggestions for how you could make this more general, then please let me know. I would love that. What we're gonna do is say that x takes values in the interval closed 0, 1. So I'm going to say x is a real valued random variable. Not so fancy. And it's in 0, 1. We could kind of change this to any interval we like, or even from negative infinity to infinity with some analysis. But I'll keep it 0, 1 because the main idea of the proof will stay the same. So my idea is really not an idea. The idea is we're going to differentiate this expression, the expected spread, with respect to c, set it to 0, and then, find a stationary point, and then look at its second derivative to see if we have a local minimum or a global minimum or something like that. Let's do it. So I'm going to say that x has a density function f, and that, that's it. So I'm going to call this expression fancy e. It's equal to the integral from 0 to 1 of absolute value x minus c times the density dx. And here, I can't integrate this directly using fundamental theorem of calculus because the antiderivative of this is a bit like, what? So I'm going to split this up. I know that x minus c is a piecewise continuous function, or the absolute value of x minus c. So in particular, this is equal to x minus c when x is greater than c, and c minus x if x is less than or equal to c. So I'm going to split the integral up that way as well, for x that is in these two different situations. So expected value is equal to, we look at first from 0 to c. In this case, x is less than or equal to c. So our expression is just going to be c minus x f of x dx. And for the other case, we do the other thing. That should be my motto. For the other case, we do the other thing. Okay, so now we could integrate each of these. Well, we could deal with this much easier. Maybe we're still not going to integrate it. Why is that we still don't integrate it? Well, we don't really know what f is. We're doing this in general. But what we could do is now shuffle things around and break up integrals even more. So ultimately, I want to differentiate this. And my main trick is going to be the fundamental theorem of calculus, which says if we have an integral of the form a for constant a to c, maybe big F of x dx, the derivative of this with respect to c is equal to big F of c. And notice here I have these c's in my bounds, so I want to be using this. I want to be putting integrals in this form, so I could use this trick and differentiate it. So let's do that. Here I have a c inside, so feels a bit nasty, I'm gonna take it out. I'm gonna take this out, and then we're left with this. This one I'm gonna take out as well. That's the first integral dissected. The second one, similar thing. Take the x, f of x. The second one, in the second term, that's going to be a minus c times integral from c to 1, f of x dx. Okay, new paper time. Oh, my paper's flying all over the place today. Nice. So, first, I'm going to notice that nothing nice has happened so far. But that we could flip this one around. So this is integral from c to 1, but our fundamental theorem of calculus is integral from something to c. So we could reverse the orientation of the integral. And actually, for the last one, we got it reversed as well. So expected value is equal to ... plus minus, because we've reversed, integral from 1 to c, f of x dx. And then plus c times integral from 1 to c, f of x dx. Okay. So now we're ready to differentiate. Differentiate with respect to c. Let's look at it. The first term, we have two functions of c's multiplied together. Product rule. So we do left d right, and the d right comes from fundamental theorem of calculus. It's just going to be f of big C plus right d left. Right is integral, left is just c, so we're just going to be left with the integral. Now for the second term, here we could directly use fundamental theorem of calculus. We get minus c f of c. For the third term is up here. We also directly use fundamental theorem of calculus. Minus c f of c. Okay, and for the last term, we again do left d right, right d left. We get left d right c f of c plus right d left. Just integral from 1 to c of f. So here, we get that this, they mutually mush together and disappear into the void. So we get that the derivative is equal to this. Surprisingly nice expression, if I do say so myself. And I do say so myself. Now we set to 0 to find the stationary point. So that means 0 is equal to the integral from 0 to c of f plus the integral from 1 to c of f. If I move this one around and I reverse the orientation of the integral, we get that the integral from c to 1 of f is equal to the integral from 0 to c of f. And since we know that the integral from 0 to 1 of f must be 1, since this is a probability density, here we conclude that c is the point such that the integral from 0 to c of f is equal to 1/2. In other words, x has half probability of being less than c and half of being greater than c. So c is actually the median. C is median. And I was hyped when I saw this, since now we have this connection between the mean and median. And it's making me a fan of the median, that this is going to be better than the mean. Because the mean is about squared error, and like I don't see why we care about squared error, and straight line error is clearly better. So yes, to finish off with this proof idea, if you have any suggestions about how to do this better, please let me know. What I mean is that this proof only works for one dimension, and I think there's some technical stuff with the fundamental theorem of calculus, like what if I had a density that wasn't continuous? Then I can't do this. And how do I fix it there? I don't really know. Thanks for your attention, and I hope you liked that. And there's a part 3 of this. Stay tuned.